Okay, y'all, finally on the last video of the semester. So in the last video that we did, we defined u plus n like that using this piecewise equation here. And what we have immediately is that for all n greater than 0, the kernel of u plus of n is going to be 0. And this is the same. This is going to be obvious. It's the same thing that we did before. If you have a non-zero sequence and you concatenate on an n-length finite sequence of zeros, if there was a non-zero term somewhere in that sequence, you're still going to have a non-zero term. So the only way for the unilateral shift to map to the n power unilateral shift to map to 0 is for the term to originally be 0. And again, you're going to get that with the dual, we have the truncation of the first so many terms. So if my first n terms are non-zero, but everything after that is 0, we're going to get we're going to end up with a 0 sequence. So the kernel of this is going to be the span of these n vectors, where this one is only non-zero in the first, this one is only non-zero in the second, this one is only non-zero in the n. So this is obviously an n-dimensional subspace, and any vector that is within the span of this guy is going to be in the kernel, because the truncation of these are going to be 0 vectors. And anything not in the span of this is going to have a non-zero term somewhere after the nth place, which means that truncation of the first n values is not going to remove all 0 terms from the sequence. So what we get for n greater than 0 is that j of u plus of n is just negative n. And that follows from the fact that this is an n-dimensional subspace and this is a 0-dimensional subspace. So 0 minus n is going to be negative n. Now, since we have that the adjoint just puts a negative in our exponent, this equation is going to follow for all n and z. So now that we have that well defined, what our next goal is going to be is to show that this is in fact a homomorphism from L2z plus to the ring Z, or sorry, the group Z. So what we're going to say is we're going to do this by cases. So if m and n are in Z, then we can split it as a homomorphism. So to prove this, we're going to proceed by cases. The first off, when m and n are both greater than 0, this should be obvious. And this follows from the fact that if I concatenate on an m-length string of zeros onto a sequence, and then I concatenate on an n-length string of zeros onto the sequence, this is the same thing as just concatenating on an m plus n length string of zeros. So concatenate on n-length string of zeros, concatenate on n-length string of zeros, we get concatenation of an m plus n length. So what this gives us is that this is really the same thing as this guy, j of that one, which would obviously be m of negative m, negative n, which is by definition our m and n, our j of um plus j of un. Now, using this same style of argument, when we consider when m and n are both negative, then they're truncations. Now, if I truncate the first m terms of a sequence, and then I truncate the first n terms of a sequence, it's just the truncation by the first m plus n terms of the sequence. So when n and m are less than 0, we're going to get that u plus of m, u plus of n is just the same thing as u plus of m plus n. So obviously we're going to get that j of u plus m, u plus n, n is equal to m plus n, which is by definition j of u plus m. Sorry, these are negatives, which is going to be j u plus m, j u plus of n, right? So we're getting that as the homomorphism holds when we have m and n are less than 0 or when m and n are greater than 0. Now, in our final case, we're going to consider when they are opposites. So the question that we're really asking here is, how does concatenation and truncation interact?